Chemistry is a really interesting topic, and for me it's because it relates to things that enter our everyday lives, such as electricity and batteries. And so I hope that you will find what we're going to be doing interesting. There will be parts that are more backgrounds, but they will help us understand what's going on in the bigger picture with electrochemistry. We're going to start talking about electrochemistry by talking about how to balance redox reactions. And in general, redox reactions will occur either in acidic or basic media. And so acidic media just means low pH and where there's extra H pluses around and H2Os. And what you're allowed to do is you're actually allowed to use H pluses and H2Os to participate in the reaction. And to participate, in the reaction. And what we're going to do is we're going to run through the process for balancing redox reactions in acidic media and basic media. And the first part will be to figure out what the oxidation numbers are. And my method for doing oxidation numbers is to organize the oxidation numbers on one row, and then there's some process work that we'll do down below. So let's see. And each element has an oxidation number. And we won't go over the rules. We've gone over the rules previously. But the rules basically say in compounds, oxygen is -2. And I see some oxygens. In compounds, hydrogen is +1. And of course, O2, which is oxygen by itself, has an oxidation number of 0 for the oxygen. But we don't see that here. Then when you get to the end of this, there should be, so there's another rule, which is monatomic ions, that's one atom ions, have their charge as their oxidation number. But we could have told that because that +2 has to go somewhere as far as the oxidation number, because another rule says the sum of the oxidation numbers has to equal the charge. Anyway, we have everything except one of the elements in each ion or compound complete. Let's go ahead and finish the last one. My process says, okay, each oxygen has a -2 oxidation number. There are 4 oxygens, so that's what I would call 4 times 2 is -2 is -8. We know that since there's a minus sign that the oxidation numbers here have to add up to -1. So the number that has to go here is +7. +7 minus 8 equals -1. And since there's only one manganese, that manganese has an oxidation number of +7. And oxidation numbers, remember, are not true charges. They are, however, a good way to keep track of electrons in redox reactions. Let's move over to the oxalic acid here. I have, again, -8. I have +2 here, and I have no charge on the molecule. So this right here must be +6. And since there are 2 carbons, each of those carbons has an oxidation number of +3. On the other side, carbon has a +4. Again, you can trace the math around and know that it's 0 total. And what we've just done is step 1. We've assigned oxidation numbers. And there will be sort of a stepwise process for doing this that continues from here. And the important thing to remember is we're not just balancing atoms, we're balancing electrons, as we'll see. And that'll be one of the future steps. So step 1, we're done. Step 2, separate into half reactions. What that means is determine what was oxidized and what was reduced. And I'm going to do that in red here. What you're looking for is oxidation numbers for elements that have changed. And I guess I'll do this one in red. +7 to +2. Well, first off, that's definitely a change. And then the numbers for the oxidation number are getting closer to negative or more negative, we would say. So it must be gaining electrons, which is reduction. Now, in another color, let's see, we see carbon, and carbon, and again, we're connecting the oxidation numbers themselves, not whatever this work is down below there. We have a +3 going to a +4. That's more positive, which means it must be losing electrons. LEO, losing electrons, oxidation. Leo the lion says, grrr. And once you've identified your half reaction, well, once you've identified the species that are being oxidized and reduced, then you can split them into half reactions. And you're going to write the whole ion or the whole formula of the species with involving the reduced species. So this is going to be manganese, or permanganate. And I'm going to leave some space here because we have some things to insert. And then Mn2+. Yep. And then for oxidation, it'll be H2C2O4 goes to CO2. Good. So step 2 is done. Now we're going to balance for mass. And when we balance for mass, for atoms wise, we get to add H pluses and H2Os. And what we're going to do is we're going to add H2O first to balance oxygens. And then when we add the H's, you can add any number of H's and it doesn't mess up any of the other elements. So let's see what we've got here. Up here, we've got 4 oxygens on the left and we've got 0 oxygens on the right. So that means I have to add 4 H2Os. And that means my oxygens are now balanced. Down here, I have 2 oxygens and I have 4 oxygens. Oh, hold on. Before I can do that, I have to balance my carbons. 2 carbons, that's a 2, believe it or not, and 2 carbons. So balance the element that is oxidized or reduced first, then balance the oxygens. So I guess I have to come back down here. 1, balance elements oxidized and reduced first. 2, add H2O to balance oxygen. 3, add H plus to balance hydrogens. Okay, so in this top one here, so now let me finish balance step 2. I have 4 oxygens and I have 4 oxygens. Phew. So far so good. Then now I have to balance my hydrogens. I have 8 hydrogens on the product side. I need 8 hydrogens, which come as H pluses here. On the next one, I have 2 hydrogens and 0 hydrogens, so I'm going to add 2 H pluses there. And so now everything's balanced except for the charges and except for electrons, because reductions and oxidations have to have those. So we'll go on to page 2. And on page 2, we've already got this set up here where we left off from step 3. So reduction I was doing in red, so I'll return to red and just to show you. So I've just gone ahead and written down what we had before. Now let's balance for charge. When we balance for charge, we're going to note that I have +7 over here, and I have +2 over here. And by balancing for charge, what I mean is add electrons and I'm going to add plus 5 electrons there. That means now minus 5 equals plus 2. And it doesn't matter what number they have that is the same, but what does matter is that whatever the charge is on the reactant side, it is the same on the product side. Down here, we have 2 plus and we have 0 charge. So 0 plus 2. And we will add 2 electrons, and then minus 2 also equals 0. And so now each of them is balanced for charge. The charges are the same, whatever that number is. And it is not a coincidence that we have 5 electrons in that reduction, because the change in oxidation number is 5. While the change in oxidation number here is 1, there are 2 carbons and 2 carbons. So that's where we get the 2 electrons from. Good. Now, next what we want to do is we want to multiply each reaction to cancel electrons. I have 5 electrons and 2 electrons. It is important, the electrons always cancel out. There will never be electrons left over in an overall reaction. Redox reactions can be thought of as electron exchange reactions, or electron transfer reactions, but there are no reactions that end up being products or reactants in the overall reaction. All right, so I have to multiply this top reaction times 2. I have to multiply this bottom reaction times 5. When I do that, I'm going to get 2 permanganates, 16 H pluses, 10 electrons, which of course we will cancel eventually, plus 5 oxalic acids, plus, that's it. Now I get 2 manganese ions. I get 8 H2Os. I get 10 carbon dioxides. I get 10 H pluses, and I get 10 electrons. Let's go ahead and cancel everything out that we can. I have 10 H pluses and 16 H pluses. That leaves me with 6 H pluses. I have 8 H2Os. I have no H2Os. I have 10 electrons. Let's just get those out of the way. And do I have anything else? I do not. Those are the only things that cancel. And now I will be left with, all right, cancel everything on both sides. Final answer, 2 permanganates, which just so happen to be aqueous, plus 6 hydrogen ions, plus 5 oxalic acids, which are also aqueous, goes to 2 manganese 2s, plus 8 H2Os, plus 10 carbon dioxides, and that's aqueous 2, plus, and that's it. I think we've run out of stuff. Phew, what an arduous process. But it is how we balance redox reactions in acidic media, and it's a 4-step process. Now, in basic media, there's another way to do it. And in basic media, you could do the same process we already did, except with, so let's say same process, except with hydroxides and H2Os. And that's one way to do it. That's not the way I do it. In basic media, I solve the problem as if we were, you were, I was, anybody, we all were together in acidic media, and then neutralize the acid H+. So this is a shortcut method for doing this because balancing with H pluses is easier. So what I mean by that, and then if you're in basic media, you will get the right answer if you take whatever H pluses you have, add an equal number of hydroxides, which are minus charged, to both sides, and then write the product, write the end reaction, and then cancel everything else that you can. This is missing some 2's from the previous reaction, so let me put those in. Everything else appears to be correct. Good. So now we have 2 permanganates plus this becomes 6 waters plus 5 oxalic acids goes to 2 manganese 2 ions plus 10 carbon dioxides plus 8 waters plus 6 hydroxides. And you'll see now we can cancel out six of the waters, and I think that's it. And I will leave this as our final answer. And again, it's just a little more tricky, so your textbook will cover how to do it with hydroxide and water. It fully works. I find this is a shorter way to do it because I've already memorized how to do balanced redox reactions in acidic media. Up to you. And note, the same reactants will often react differently in acidic and basic media. This doesn't mean that this is the reaction that occurs, and you'll be presented with the reduction and or the species that's reduced and the species that's oxidized, and then you will be asked to balance it in either acidic or basic media, like so.